This is the third video in our NMR lecture. In this video, we'll examine the chemical shift of our signals in our spectra. Looking at a table of possible shifts for different functional groups, we can see that our NMR spectra starts at 0 ppm, and it goes all the way till 12. If we remember from our first video, the peaks closer to 0 are considered more shielded, and the peaks further away, closer to 12, are considered deshielded. When we consider peaks that are shielded to deshielded, we're really looking at about how much electron density is around that hydrogen. The more electron density we can see around the hydrogen, the more shielded the proton is. All NMR spectra have a reference point for 0 ppm. The reference is TMS, and it is always set at 0.0 ppm. This is to mean that TMS, or trimethylsilane, is considered the most shielded of protons that we have. Every other proton we look at is more deshielded than trimethylsilane. So we can see about 0 to 2, that's where we have our carbon CHs. These are sp3 carbons with just other carbons or hydrogens attached to it. Then we can see around 1.5 to 3, we have some hydrogens that have a carbon with something else attached to it. This something else that's attached to our carbons could be an aromatic ring, a nitrogen, sulfur, triple bond, or it could be a carbonyl. So we could have our carbon with a carbonyl directly next to it. Then even more deshielded protons have something that's considered electronegative, or something you can think is like electron withdrawing, or your electron withdrawing groups from your aromatic substitutions. Those are a good correlation here. So you can see it's typically halogens, oxygen, or a nitro group will start making that proton even more deshielded. Then we can also see anywhere between about 0.5 to 5 ppm is where OH or NH show up. This range is so large because the OH and NH are more variable and depend a lot more on the pH of the system and the pH of the solvent. But one way we can always tell the OH and NH is they're typically broad peaks. Your CHs are typically really sharp peaks, and the OH and NH tend to show up as a much smaller, broader peak, but it'll still integrate to one hydrogen. And we'll talk about integration on the next video. Then we move further and we have our alkene protons. These are protons that are directly attached to the double bond. They show up anywhere from 4.5 to usually about 6.5 or 7 if there's something really electron withdrawing on that double bond. Then finally, between 6.5 and 8, that's where aromatic hydrogens show up. This is usually a very distinctive region to determine if you have an aromatic ring or not. There's usually a little bit of a gap, and then between 9 and 10, that's your aldehyde H. You can see the aldehyde H acts differently than our alkene hydrogens. It's much more deshielded because of that oxygen present. And then finally, our most deshielded protons are carboxylic acids. The carboxylic acid, OH, tends to show up as a very small, very broad peak. And so sometimes the carboxylic acid OH tends to be so broad that it's very hard to see in the NMR spectra, but the machine will integrate something in this region for you, and then you can tell you have a carboxylic acid OH. So this looks like a lot to learn, a lot to memorize, but don't worry, you don't have to memorize all these different pieces here. Instead, it's usually better to kind of look at different regions in the NMR spectra. So if we just look at the different regions, that can help us figure out kind of a quick idea of what functional groups we might have before we interpret the spectra further. So you can see between 0 and 2, that's where our saturated hydrogens typically show up. So these are our CHs when our carbon is sp3 hybridized. The region between 2 and 4, we typically have something that's electron withdrawing connected to the same carbon as the hydrogen we're looking at. The more electron withdrawing the group, the more deshielded that proton is, and the higher the ppm. And then our region between 4.5 and about 6.5 is where our vinyl hydrogens show up. So this is going to be your alkene region. Slightly higher than the alkene region, usually between 7 and 8, you'll see your aromatic protons. Then there's usually a gap followed by your aldehydes, which typically show up around 9 to 10. And then finally, anything above 10, you can start to think you have a carboxylic acid present. Now, all of these are just regions. If you have something very electron withdrawing on your aromatic ring, you may see peaks above 8. So if you see something slightly outside the regions here, that's okay. So now let's look a little bit closer how the electron density affects the different ppms. So if we consider a methyl group and change what is attached to it. So you can go from something that's fairly electron donating or kind of a neutral atom, a hydrogen. And then if we add an iodide, we know that iodides are slightly electron withdrawing. Bromines are typically more electron withdrawing than iodides, followed by chlorines. And then we all know fluorine is the most electron withdrawing atom we have. You can also see this kind of follows the trend of the electronegativities. The more electronegative the atom, the more electron withdrawing it is. So you can see this also follows the trend of electronegativity. The more electronegative the atom, the more electron withdrawing, the group is, and the higher the ppms are. So now that we've kind of seen that idea a little bit, let's look at what happens when we add more electron withdrawing groups on the same atom. So here we're comparing our methyl group still, our carbon, and we're adding an increasing number of chlorines to it. So at first we start with 0 chlorines. A methyl group will typically show up around 0.23 ppm. And then adding 1 chlorine to it, we see the ppm shift up to 3.12. If we add a second chlorine, the ppms increase again to 5.3. And then finally adding a third chlorine to get chloroform, the ppms increase to 7.24. The more electron withdrawing groups you add to it, it has an additive effect to increase the deshielding effect and increase the ppm. And then so looking at a final trend, we're going to look at what happens when we increase the number of alkyl groups. So here we're changing the hydrogens and adding in more carbons. So we're going to add more methyl groups to our central carbon here. If we start with just methane, we see that would have a much lower ppm. Adding 1 carbon group to it. So we have a slightly more substituted carbon in the middle. That increases the ppm a little bit. Adding a second carbon group will increase it even further. And then adding the third carbon group will increase the ppm even further. So each time you add a carbon group, you're increasing the deshielding effect. It's not going to be as dramatic of an increase as when we're adding the electronegative atom. Here, the increase might go from 0.23 up to about 1.5. So it's not as dramatic of an effect, but you can still have an effect. So the more substituted your carbon is, the larger the ppm. So now that we've looked at a couple trends and we've looked at our chemical shifts, let's look at a couple of spectra to examine these. In our first spectra here, we're looking at an aldehyde an aromatic ring, and a methyl group. It's very important to be able to distinguish your functional groups at this point. So if we remember, our aldehydes typically show up between 9 and 10. And we have a peak right around 10 for our aldehyde hydrogen. Aromatic rings typically show up around 7 to 8. And we can see we have 2 peaks here. If we remember our review for our types of hydrogens, in a pair substituted ring, there's 2 types of hydrogens, so we see 2 peaks in the spectra. And then our final group, our methyl group, that's connected to the aromatic ring. Since it's connected to the aromatic ring, it has a slight electron withdrawing effect on it. And so you can see the methyl group is going to show up around 3.5. So this way we can identify all the peaks in our spectra with only knowing the regions and not knowing all the specific details. So let's look at another example. So in this example, we have an alkyl group and an OH. So we have an alcohol, and then we have sp3 carbons. So when we're trying to identify the difference between the carbons and the alcohol, remember alcohols are typically broader than your CHs. So our alcohol group is going to be this peak right around 2. And then breaking down our CH groups a little further so we can try and identify more of those peaks. We can see this CH group, that CH2 has an alcohol connected to it. Since it has that oxygen, that's going to be much more electron withdrawing than the other 2 groups. So that means that's going to be our peak around 4, around 3.54. And then we're going to look at our peaks for CH2 and then our CH3. The CH2 has more substitution on it versus the CH3. That means it's going to be a little more deshielded. So that CH2 group is going to be that peak. And finally, the CH3 will be our most shielded peak, closer to 1. So again, you can see we can identify all the peaks just by kind of knowing the regions and knowing the trends of how the shifts happen. So let's look at one final example for our chemical shift segment. For this segment, we're going to look at benzoic acid. Benzoic acid contains a carboxylic acid group and then an aromatic ring. Carboxylic acids, as you can see, show up close to 12. This happens to be a very well-defined carboxylic acid group. More typically, your carboxylic acids tend to be just a small peak like that. So don't be fooled by seeing a really good peak here. Typically, they're much smaller. And then finally, we look for the aromatic ring. We can see we have peaks between 7 and a little bit above 8. Like I said before, if it's a little outside the typical region, that's okay. It's very difficult to identify which one of these peaks corresponds to which hydrogens on the ring. So we can just say the ring is going to be both of those peaks. So now you guys should be able to identify the peaks in your main areas of your spectra and determine which functional groups are associated with those peaks. You should also be able to start identifying which CH groups are which peaks in your NMR spectra.